Oh, by the way, I'm saying that the way forms work is we can only integrate them over the appropriate object. Like a 1 form has to be integrated over a curve, a 2 form has to be integrated over a surface, a 3 form must be integrated over a volume. That's how we define integration. All right? A 0 form can only be evaluated at points, actually, because points are 0-dimensional objects. That's the structure of the integration of forms. What do you guys think I should put here? Something we've already talked about this semester, something that you're nearing comfort with before test 4, right? Don't put it off till Thanksgiving. You're going to be sleepy. Figure it out before then. Yeah? There we go. It is exactly the surface integral. Now, of course, our notation in here was like that, right? But I'm not going to write double integral over here. Okay. But yes, it's the surface integral. That is the integral of a 2 form. What do you think now this is a little bit trickier, but the integral over a volume of like f dx wedge dy wedge dz is actually equal to the integral over the triple integral over the volume of f dx dy dz. Notice, so in the triple integral, what's going on here is we're just dropping the wedges and doing an ordinary volume integral. The difference between this and that is profound, though this is an oriented integral. If I switch the order of the wedges, you can get a minus. So this can be, there's an orientation to the form integral, which is not present over here. And so like this has to be done with respect to a choice of orientation for the volume. I don't want to get too technical about it, okay? So that's integration. So you already know how to integrate forms because you already know how to calculate line integrals and all that. But there's something more. There is a theorem known as the generalized Stokes theorem. All right? And what does the generalized Stokes theorem say? It says for a space M with boundary partial M, we have, and I guess I should be more clear here, a p-dimensional space. P-dimensional space M with boundary partial M. We have that the integral over M of d alpha is equal to the integral over the boundary of M of alpha. You can almost think of the generalized Stokes theorem as taking the exterior derivative of the form and transferring it to a derivative of the space in that sense. Now, for this to make sense, what kind of form am I looking at? Like if this is p-dimensional, right? Then this must be a p form, which means alpha must be a what? P minus 1 form. Alpha. So we know that the integral over a curve of df should be integral over the boundary of the curve of f. So if I think about a curve going from, say, point P to point Q, right? then this translates into the integral over the curve of the work form of the gradient of f is equal to the integral over this, boundary of the curve of f. Now this way this is equal to the integral over the curve of the gradient of f dot dr is equal to, what's this? Well, this is f of, the boundary of the curve is actually basically q minus p is the way it works. And so when you evaluate that, you get f of q minus f of p. That, my friends, is the fundamental theorem of calculus for line integrals. So the generalized Stokes theorem in this context is the fundamental theorem of calculus for line integrals. But if we can play this game for the derivative of a 0 form, we can just as well play the game for the derivative of a 1 form. Right? What's the exterior derivative of a 1 form is a 2 form. Right? And so in order for that to make sense, I have to integrate over a surface, you see? But the generalized Stokes theorem says that's the integral of the boundary of the surface times omega f. Well, on omega f. But what are we looking at? This is the same as the integral of the flux of the curl of the vector field over the surface is equal to the integral over the boundary of the surface of omega f. But then translating that into line integrals and surface integrals, that's the surface integral of the curl, right, is equal to the integral over the boundary of the surface. That is, of course, Stokes theorem, right? So the generalized Stokes theorem naturally includes Stokes theorem. There's one more interesting case to look at here, which is the case of the exterior derivative of a 2 form, which would be over a volume. d phi f, right? Integral of the boundary of the volume of phi f. Oopsly doopsly. Is that right? Oh, yeah, that's good. So that's equivalent to what? The integral over the volume, excuse me, the integral, my bad, integral over the volume of the divergence of f dx wedge dy wedge dz equals to the integral over the boundary of the volume of phi f. All right, so then translating that into ordinary integrals, what do we have? We have the triple integral over the volume of the divergence dx wedge dy wedge d, well, no wedges here, just dx dy dz is equal to the integral over the boundary of the volume of f dot ds. You should recognize this. This is the divergence theorem. So in fact, the fundamental theorem of calculus for line integrals, the Stokes theorem, the divergence theorem, these are all just different faces of the same theorem known as the generalized Stokes theorem, which I think is very beautiful. And the thing that's really neat is this isn't special to 3 dimensions. Like the thing we do with vector fields and surfaces, right? The fact that we can calculate both flux, this has been troubling to you in this course if you think back on it. You've all struggled with this. Because at some point you've gotten confused. You're like, wait a minute, are we calculating a line integral or are we calculating a flux integral? What am I supposed to do with a vector field? Because those are two totally separate notions of integration. Curve versus surface, right? And the reason that you're able to do that is because there's a very special accident that happens in 3 dimensions, namely that 1 forms and 2 forms are interchangeable by Hodge duality. So there's this interlinking of surface and line integrals that's not present in higher dimensions. But the exterior calculus is not just a 3-dimensional thing. You can set up exterior calculus in 4 dimensions, in 5 dimensions, in 6 dimensions, whatever. So if you talk to like modern theoretical physicists, you'll find that the calculus that they do is the calculus of differential forms. This is the stuff that string theory is written in and things like that. It's also the mathematics that you need to study fluid dynamics, because fluid dynamics are naturally understood in terms of curved spaces and higher dimensional things, actually. And so this math is also touched on there. So anyway, this is it for Cartesian coordinates. That's pretty much the end of, I mean, you could ask interesting questions, right? Like, what if you try to combine the product rule with the integration we're doing? What would integration by parts look like for forms? What are those theorems? Do we even know those theorems in vector calculus, right? Ever thought about this? Is there an integration by parts for like the divergence theorem? Well, we could investigate that from this perspective. Any questions? So I'm not sure the exact history of this, by the way, but I think Cartan, I mean, it's not much older than this, maybe Civil War. So I'm sorry, War between the states, War of Northern Aggression. Excuse me. Oh, wait a minute, went too far. Maybe, I don't know. Anyway. Oh, name. Put your get a piece of paper out. Write your name at the top. Right. Surprise attack mission. What are we on? 14. Surprise attack mission 14. Pass them up. Yeah, just name. If you can write your name, then that'll do. I was going to ask you guys the question. This was what I was going to, but I forgot, so it's too late now. I was going to ask you guys, F equals to rho hat over rho squared is the curl of A. Find A. That was going to be the surprise attack mission today. I had every intention of asking that. Maybe I'll ask it tomorrow. Can you solve that problem? What do you guys think? Are we going to be able to solve that problem with differential forms? I wonder. We'll find out.